Throughout the remainder of this section, we're going to be looking at two additional ideas that we can use to try to help us tackle some questions about convergence and divergence of series a bit simpler. In this first theorem here, we'll see that if we have two convergent series, an A sub n and a B sub n series that are convergent, then we can reach some conclusions about some other series. What we'll be able to see is that the series, which is written as C times A sub n, where C is a constant, and the series where I have my A sub n added or subtracted to my B sub n. If I have these series, then these series here are also convergent. So if these first two series add up to something, right? Like maybe the first series here, just for the sake of example, right? Maybe my first series here adds up to 6 and my second series adds up to 5. Well, this series is going to be able to add to something else, and this series is going to add to something else. I don't really know what they might add to, but I know they add to something. I know they're still convergent. However, if we continue on with this theorem, we'll actually be able to see that we can replace these question marks with something more specific. First off, we can see here that if I was to look at the addition and subtraction of my two series here, I can see that this is actually going to be identical to my series with A sub n, just plus or minus my series with B sub n. So that would kind of mean that, like, if my first series added up to 6 and my second one added up to 5, then this one here, if my two things were added, would have added up to 11, and if they were subtracted, they would have added to 1, or I guess subtracted to 1, right? So I can see here that I either am going to have 6 plus 5 and make 11, or 6 minus 5, which would make 1. And that's going to give me the total value for this series. I can also see that if I have my series C times the A sub n, that is actually going to be equal to taking that C and bringing it outside of the series and multiplying on. Meaning that, like, if my constant here was some number, then if that original series was going to be equal to 6, then this would just be equal to 6 times whatever C is. So this is a really, really powerful set of properties, but notice it only works for convergent series. It's actually true, though, that this last property can be used with most divergent series that we're going to be seeing in this class. And so you'll often see us pull constants out of series that are divergent as well. We'll talk more about that in some specifics a little bit later. But let's take a look at how we can use these properties here in something like example number 3. Okay, so here I want to determine with justification whether the series that's written here is convergent or divergent. And I want to find its sum if it is convergent. Well, I'm going to go ahead and just quickly note that, first off, these terms in here are very awkward. But I do notice that there seems to be this alternating pattern occurring in the top. And so immediately I'm going to go ahead and start to maybe kind of color coordinate these. You'll notice that I have red terms that have 1s in the numerator, and I have blue terms that have 2s in the numerator. I'm going to go ahead and think about rewriting what we have here. So I'll say we will rewrite the series as 1/3 plus 2/7. I'm going to put that in a set of parentheses. And then I'm going to do my 1/27 plus my 2 over 49. Then I'm going to do 1 over 243 plus 2 over 343, and go on and on and on. So I've only really just kind of introduced these sets of parentheses here. But notice that by doing this, I've kind of grouped together a kind of a collection of blue and then red items. Now, is there a connection between all the red items besides just the fact that they happen to have a 1 in the numerator? Is there any way I can imagine building from one red item to another? Well, if you play around for a little while, you might be able to notice that I can actually get from one red thing, to another red thing by actually multiplying by a value of 1/9. And I can get from one blue thing to another by multiplying by a different value. Can you tell what it would be? Yeah, 1/7. You could check the same thing as you continue on down the line. Well, a series that continually multiplies by a same common value is actually a geometric series. So I'm actually going to claim that this is going to be equal to the sum. We'll have here, say, k starts at 1 and goes to infinity, and I'm going to write out kind of like a red geometric series formula plus a blue geometric series formula. Notice that the red one would be simple. Remember that a is always going to be the value I start with, and then I'm going to have 1/9 to the k minus 1. The blue starts with 2/7, and then I'm going to have 1/7 to the k minus 1. Now, if I want to find if this converges or diverges, I first have to note that by itself, this is not a geometric series, right? This is not here, when I combine my blue and my red, an a times an r to a k minus 1. That's not what I have. However, can you kind of tell I have something like this first bullet point in the box above? I have like one formula added to another. And it would be great if I could break these apart and then just add their resulting sums together, like we did with the 6 and the 5 to make 11. But that only works if the series are convergent. So let's see. I'll state here that each of our series here, I'll write these out separately. This series and this other series, if I had them as separated series, are convergent geometric series since the absolute value of r is less than 1 in both cases. So I know that these are convergent. I kind of met the check to use this theorem. And so if I continue my equal sign down, I know that I can actually re-express this as the sum of the two series that I had up above. So that is, I'm connecting these pieces here by saying that I can actually add these two together. I know these should be equal. And that's very convenient because since these are geometric series, I know that the first one adds up to a over 1 minus r, and the second one adds up to a over 1 minus r. That, of course, is the same thing as, let's see, 1/3 over 8/9 plus 2/7 over 6/7. And I think if you do a little bit of work and continue to clean that up, you can get down to a final answer here that would end up being something like 17 over 24. I'll leave that for you to go ahead and try to confirm on your own. But I can see how this interesting theorem here allows us to take, again, different series that are separately convergent and start to understand how to deal with combinations of those, as well as with some constants.